Hi all, I'm excited to go through your midterm practice here with you. If you took a look at my individual tests that I had given in previous semesters, my test 1 and test 2, what's on this midterm practice and what will be on our midterm exam should come as no surprise. All I've done is I've taken the 2 tests that I would have given about every 3 weeks in previous semesters and combined them. And of course, since I can't make too long of a test, I've had to filter out a few problems. It's so hard to filter out problems though. So this is a rather long test, but since we only have 2 tests this semester, it shouldn't be surprising that the 2 tests will be, relatively long. Looking at your first problem on here, and please keep in mind, each problem on here will have an accompanying very similar problem on your actual midterm. So I guarantee you your first problem will be an absolute value inequality. In this one, I'm looking at the absolute value of 4x minus 5, and it's less than 11, greater than, strictly greater than 11. So I know that if 4x minus 5 is a positive number, that positive number is greater than 11. However, what an absolute value enables, since it's going to make whatever's inside of it positive anyway, if it's a negative number, in order for this original to be true, that negative number needs to be less than a negative 11. What you can remember in all of these problems, if you keep what's inside the absolute value and you keep the sign of the other side, then you're going to keep the direction of the inequality. If you change the sign of the other side, then you have to flip the inequality. Now, please keep in mind, this inequality is flipped in regards to the 4x minus 5. Here it says 4x minus 5 is greater than 11. Reading backwards, it says 4x minus 5 is less than negative 11. Now, solve for x. So we say we'll add 5 to each part of our inequality. That gives me negative 6 is strictly greater than 4x, which is strictly greater than 16. Then I can go in and isolate x by dividing by 4 everywhere. And then, of course, that should be reduced down. X is going to be less than a negative 3 over 2, but greater than 4. So now I need to think about my interval notation solution, and I would not give full credit unless I see this. So this would be probably worth half credit. The remaining half, I want to see the interval notation. A lot of students would struggle getting to this. And if you just think about what this means, well, x is a number less than negative 3 over 2. Well, that means it can go all the way down to negative infinity. Any value from negative infinity up to negative 3 over 2 satisfies that criteria. But then x could also be a number greater than 4. So you say, well, that's union starting at 4, not including 4. That's why you see a parenthesis all the way up to infinity. So our final answer there, in interval notation, negative infinity to negative 3 over 2, union 4 to infinity, parentheses around everything. Please keep in mind, the only thing that would have changed if this would have been greater than or equal to is I would have had brackets around both the negative 3 over 2 and the 4 because they could have been included in the answer. Okay, up next, probably one of my favorite problems on this test, just because of its importance in Calculus 2, I want you to be able to complete the square. So I gave you y is equal to 3x squared plus 28x plus 13, and I said rewrite this by completing the square and then state what the maximum or minimum would be. Okay, no problem. In order to complete the square, I need a perfect square trinomial. I can't get a perfect square trinomial. Whoa, that's too bright. I can't get a perfect square trinomial as long as that first term is not a perfect square. So I had no choice here. I had to factor that 3 out. So the 3 came factored out in front, and then please notice the x squared, if you factor a 3 out of this, you're going to have 28 over 3x. Now, the red is just where I left a space there initially. I just said I know I'm going to have to add some constant there, but I don't know what it is yet. I knew it wasn't the 13. Notice I just separated the 13 from the terms of x. I did not bother to factor a 3 out of the 13. 13's just out there all by itself. Now I look inside this group, there was a blank there, and I said, well, how do I fill in that blank space? I need a perfect square trinomial. Every single solitary time, if you need a perfect square trinomial, the term for c that you need is 1/2 of b squared. So you say, well, 1/2 the coefficient of x would be 14 over 3. Now I need to square that. 14 squared is 196, 3 squared is 9. I need to add a 196 over 9 inside of that trinomial. Now, I can't just go through adding a term to a side of an equation without making up for that. Now, I need to leave the other side y. So please don't say, well, why don't you just do something to the left to make up? Because that needs to stay y equals. Now, on the right-hand side, then, I'll make up for it. If I put a plus 196 over 9, I subtract 196 over 9. Now, why did I subtract 196 over 9 times 3? Well, because this adding 196 over 9 is also multiplied by 3. That's a common mistake students will make, is they'll add the 196 over 9 inside this group and think they're making up for it by subtracting it and forget that this one's multiplied by 3. That means this one has to be multiplied by 3. So now, with the red in there, I know what I have is equivalent to what I have, but it's in such a better form because now I can say, well, this perfect square trinomial can and should be written as the binomial x, so it's always the square root of the first term, and then you keep this sign plus, and then you can either say it's half of b or the square root of c. The two numbers are the same. X plus 14 over 3 quantity squared. When in doubt, you could FOIL out x plus 14 over 3 times x plus 14 over 3. I promise you, you'd get that trinomial back. So this is equal to this part. Now, the other part, plus 13 minus 196 over 3, that's simplified to give me minus 157 over 3. And of course, I just did that on the calculator. Although it wouldn't be hard to do by hand, you'd have 39 over 3 minus 196 over 3 for the minus 157 over 3. Now you're supposed to look at this and say, well, this is just a parabola that's been shifted 14/3 of a unit to the left and down 157 over 3 units. And it's going to be pointing upward since it's a positive parabola. So the vertex is going to give you a minimum. We're going to have that minimum at negative 14 over 3, comma, negative 157 over 3. Pretty nice problem. Okay, for the next one here. I'm wanting to make sure you can solve out exponential equations. So the goal to any exponential equation is to get the exponential base by itself, and then to take the log of that base of both sides to simplify. Okay, so I need to get the exponential base 7 all by itself, okay? First step, get rid of that denominator of 5. I multiply by 5 on both sides. So now I get 7 to the 3x minus 2 is equal to 40. Add 2 to both sides. 7 to the 3x is equal to 42. Here's where some students would make a bonehead mistake and say, hey, do I need to divide by 7 on both sides? That'd be horrible. That's not 7 times 3x, it's 3x in the exponent of a 7. So you say, well, okay, how do you get rid of that exponential base of 7? The only way to get rid of it is log base 7. Now, well, I shouldn't say the only way, the best way. Alternatively, you could have just said, well, John, I'm going to take the natural log of both sides and then work it out. That's okay. This is emphasizing the fact that logarithms and exponential bases are inverses. Log base 7, exponential base 7 to the 3x, and I take the log base 7 of the right-hand side. Log base 7 of exponential base 7, log and exponential are inverse functions. They undo one another. So now my left-hand side is simply just 3x. On the right-hand side, the log base 7 of 42, Some of you have calculators where you can evaluate that. So if you wanted to leave it as that, you could. Otherwise, you can just say, well, change a base formula. Log base 7 of 42, it's equal to the natural log of 42 divided by the natural log of 7. I went ahead and used the change of base just to make sure anyone could do it, no matter what calculator they're using. Now, in order to solve for x here, of course, you need to divide by 3. So I would have the natural log of 42 divided by 3 natural log of 7. That would be my final answer here. Now, here's something, unfortunately, I see students do wrong quite often. They'll say, hey, I got this answer, but I'm not getting the decimal. Think about what I'm doing wrong right here. If I say the natural log of 42, and I'll divide that by 3 natural log of 7. This is wrong, hideously wrong. And you think, well, why is it hideously wrong? What you have to understand is that denominator needs to multiply before it divides into the numerator. What this is it's the natural log of 42 divided by 3. Then it's going to take that answer and multiply by the natural log of 7. That's not what I want, but that is what I literally told my calculator to calculate here. It will do order of operations, division and multiplication in order from left to right. So it's dividing the 3 before it's multiplying the natural log of 7. So if you do it out this way, you would have to say the natural log of 42 and then divided by the group 3 natural log of 7 like that. Boom. And you can get the 0.64 rounded to 3 decimal places. This would just be 0.640 or 0.64. Alternatively, you could save yourself some effort. If you have one of the 84s with a more recent update, you can hit alpha y equals and it'll bring up the fraction. Alpha y equals enter. And then you can just say, well, it's the natural log of 42 divided by 3 natural log of 7 without having to remember to put parentheses around the denominator, because once it's in a quotient form like this, it knows to simplify the numerator and simplify the denominator before dividing it out. And you get the same 0.640 answer. Okay, so now either way should get the right answer with that. And by saying either way, you could have also, I'll show you the other way. You could have left it like this. That is math log base. And you can do log base 7 of 42. And then you would be taking that answer and dividing it by 3. This will be that same 0.64 answer. Nice. But for me, I kind of prefer you to use the change of base formula. But the other's okay. Now, the next absolutely cool problem, and the reason that I say this is an absolutely cool problem is because of the necessity to be able to rewrite the composition of trig and inverse trig functions as an algebraic function. The reason that this is so needed is because in this class, if I say, hey, can we take the derivative of this? Sure, no problem. We will be taking the derivative of functions like that. What about whenever you start integrating in Calc 2? Is anyone that I even know of capable of integrating that in its current format? The integral of the tangent of the inverse cosine of 3 over x with respect to x. Nope. I can't think of a soul, and I know some brilliant mathematicians. I can't think of a soul that could integrate this. So you say, well, okay, then if you can't integrate it, what do? You have to rewrite it as an algebraic function and then rewrite it. So we need to understand the composition of a trig and inverse trig function. It's just an algebraic function. We need to find that algebraic function. So we know that any inverse trig function in existence, it's merely just an angle. Therefore, there is no problem with just letting an arbitrary angle theta represent the inverse cosine of 3 over x. That's all we're saying. We're saying, well, whatever that inverse cosine of 3 over x is, it's just an angle. We're going to name that angle theta. Now, what do we know about angle theta that's equal to this? Well, you know you could take the cosine of both sides of this equation, and the cosine of theta would equal 3 over x. Cosine and inverse cosine cancel since they're inverse functions. So now you can say, well, the fact that I know that the cosine of theta is 3 over x, what does that tell me? Please remember, right trig triangle, SOHCAHTOA. Cosine is the ratio of adjacent to hypotenuse. So I draw a right trig triangle, and I'll label this the angle theta. Well, adjacent to angle theta has to be the side 3. The hypotenuse of that right triangle has to be x, adjacent over hypotenuse. Now, what's the opposite side? Well, we know the opposite side is just a leg, and any leg is always the square root of the hypotenuse squared minus the other leg squared. So this goes back to a squared plus b squared is equal to c squared. I'm just saying b is equal to the square root of c squared minus a squared. So now I can say it's the square root of x squared minus 9, and please don't make the silly mistake and call that x minus 3. Some students have a bad habit of doing that. You can't take the square root across a sum or difference, so you say that's as simplified as we can get. Now I go back to my problem. I've allowed theta to represent the inverse cosine of 3 over x. So the tangent of the inverse cosine of 3 over x is equal to the tangent of theta. Well, now we know information about theta because we let theta represent that. Well, what's the tangent of theta? The tangent of theta would be opposite over adjacent. So I can say, ooh, opposite over adjacent, the square root of x squared minus 9 over 3. Glorious. Final answer. And would we be able to integrate this in the next class? Oh, you betcha. And it wouldn't even be that hard. Whereas the original format, whew, brutal. Now, the next question I absolutely adore too. Well, I like them all. Number 5 here, I'm asking you to tell me the two values on the unit circle such that the tangent of theta is equal to -2. On the unit circle from 0 up until 2 pi. Now, whenever we think about how to do this, because this is not some angle that we're supposed to be familiar with. You're not just supposed to know, hey, when is the tangent of theta -2? You don't know. It's not any exact nice angle. It's going to be some irrational radian angle. And I do want the answer in radians since I said between 0 and 2 pi. Now, most people, without thinking about it, they'll just say, oh, cool, I can solve for theta. I just take the inverse tangent of both sides. Theta is going to be the inverse tangent of -2. They would go to their calculator kind of without too much thought. Now, hopefully you would think that it needs to be in radian mode, but then they would just go in and say, well, it's the inverse tangent of -2. Boom. Yay, I'm done. -1.107. Here's the gorgeous thing about this problem. You put that answer on my test, you get 0 credit. You're like, oh, well, jerk, why? Why would you get 0 credit? Because that's not answering the question I asked. I asked for the two angles between 0 and 2 pi. So the problem here, the inverse tangent, it's only capable of giving me an answer between -pi/2 and pi/2. The reason is because the inverse tangent is created from the one cycle of the tangent function from -pi/2 to pi/2. So it's only capable of giving me an answer in through there. So it's giving me this angle right here. Well, it's giving me a coterminal angle to this angle right here. It's telling me the angle is -1.107 radian angle. That's the angle at which the ratio of the y value is going down twice as much as the x component's moving to the right. Well, okay, that is when the tangent of theta is -2, but that doesn't answer the question I asked because I wanted an angle between 0 and 2 pi. Now, you'll see I have this drawn out here. If we want the tangent to be -2, the angle has to go down closer to the vertical axes of pi/2 and 3 pi/2 than the horizontal axes. And that's because the y value is going down twice as much as the horizontal value is moving over. It's also in quadrant 2 because I could say, well, the tangent, it's the ratio of opposite over adjacent. So I could move to the left 1 unit and move up twice that amount of units. And again, I'm at an angle at which the tangent should be -2. Okay, how do I find those angles? Well, what we're supposed to know is the angle the calculator gave me was this one. And I said round to 3 decimal places. So if I wanted to find θ1 first, I can say, well, this angle is -1.107 radians. To get to that same position in quadrant 2 where the tangent is -2, I just need to add pi radians. It's going to be half a revolution away from that. Now, you don't have to take my word for it. You can check yourself too. So here I know this is the answer, but notice if I did it on the calculator and I wanted to check, I'm trying to get away from the glare. There we go. I could add pi to that answer. That'll get this answer right here. Now, I should be able to take the tangent of that answer, and the tangent of that answer better give me -2, or I'm wrong. Let me see if I can clear this up a bit. Not too good. Or I'm wrong. And hey, if I'm wrong, we won't have the test. But I'm right. Gorgeous. So we say, okay, you proved your point. I know that an angle of 2.034 radians will have a tangent of -2. Now, my other value, it's the same angle as this -1.107, but I said only angles between 0 and 2 pi. So you say, well, coterminal to that -1.107 is if I just add 2 pi radians. So I'll go back and get that answer. Inverse tangent of -2 gave me that. If I add 2 pi radians, gives me this. I better be able to take the tangent of that answer, and this better give me -2, or I've proven myself wrong. But I've proven myself right, actually, because it is -2. So then you're like, well, cool, that is a gorgeous trig problem. I think so. I love that problem. Up next, so this is my pre-calculus review. We have 3 basically what I would call algebra basic problems, and then the 2 trig problems. Now starting what would be chapter 2 in our book with the average rate of change of a function. If I say f of x is equal to 1 over x plus 2, and I ask you to find the average rate of change from 2 to 2.1, then you can say, well, average rate of change, that's just the change in y over the change in x. It's the ending point minus the beginning point, or sorry, the ending y value minus the beginning y value, f of 2.1 minus f of 2 over the ending x component minus the beginning x component, 2.1 minus 2. So then you can say, well, clearly the change in x, it's going to the right 1/10 of a unit. F of 2 is never going to change in any of these, and that's just 1 over 2 plus 2, that's 1/4 or 0.25. F of 2.1 here, that's really easy to figure because you can just say, well, it's going to be 1 over x plus 2, 1 divided by 2.1 plus 2, that's just going to be 1 over 4.1. That's where I'm getting that first number. Please don't round that number at all. It's going to mess you up if you do. So now I would need to subtract 0.25 from that and take that answer and divide it by 0.1. You'll see I got this right here, the -0.0609756098. Now for the second one here, I just had to find out the only thing that changed was my denominator. It's only going an increment of 1/100th of a unit. My numerator, f of 2.01, that's just going to be 1 divided by 4.01. That leading y value right here, I would subtract 0.25 from it, divide that by 0.01, and I'm getting this number. Now, This problem, it's a little harder to see the pattern in this problem as unlike it is in some, but there is a pattern, and here's what I want you to do to see it. Please think about what the change in the first average rate of change formula answer to this average rate of change formula answer. You can say, well, the first two decimal places are the same, so 0.00, and then you can see the change from here to here. So you say, well, this increased from 9 to 23. 23 minus 9 is 14. So this increased in a negative direction by 0.0014. Now, without even looking at the next one, and we'll go to our next page in a minute for the next average rate of change, I'll already make a prediction, and I guarantee you this prediction's right. That same pattern is going to continue, but just as that rate of change is going to get by a tenth closer and closer and closer, then whatever the pattern is from this number to this number, it's going to decrease by a tenth of the factor. So what I'm saying is, if this number to this number increased in a negative direction by 0.0014, then when I go from this number to the next one, it's going to increase by 0.00014. So without even looking at the next page, I'm predicting that the next value, instead of 34 here, it's going to have 48. So the next value is going to be negative 0.06248. Let's see if that comes to pass. Oh, it's going to. Gorgeousness, oh gorgeousness. And I did not know that. I didn't remember. I just knew from the way these numbers patterns work. So whenever I go in here and I can plug these values in, do the same thing, divide by 0.001, I see it's approaching negative 0.06248437889. Now, if this pattern keeps on and on and on going, like what's the next one going to be? Like if I said, what's the average rate of change from 2 to 2.0001? You'd say, well, you'd add a 14 right here. It'd be negative 0.0624, and then 98, and then that 8 would later become a 9. So you'd say, well, this is going to become negative 0.062499999999. It's approaching negative 0.0625. That's what the instantaneous rate of change is getting closer and closer and closer to. Now, if you had any doubt and you wanted to graph it out, I didn't really mean to make a rhyme there, but kind of glad that I did. You could do it this way. Notice if I go into my calculator here and I wanted to graph the rational function 1 over x plus 2, and I'm interested in what the instantaneous rate of change at 2 is. So I can say, well, all right, and guys, I'm sorry, this glare, it's not great on the screen, but I think you can still see it. I'll go, let's go zoom 6. That'll be good enough. It's not going to be a great picture of it, but it's adequate. So what I'm looking for is the instantaneous rate of change at x equals 2. And I already said, hey, it's negative 0.0625. Now, just by looking at it, that should make sense. You say, well, it's decreasing, but it's not decreasing very rapidly by the time you get to x equals 2. It's pretty much flattened out. If I test that, second, calculate 6, and then you hit x equals 2, please notice it's saying the instantaneous rate of change, dy dx, the instantaneous rate of change of y with respect to x at the instant x is 2, is it's going down at a rate of 0.0625 y units per x unit there. Gorgeous stuff. Now, back to this. You say, okay, from that, we want to go to the algebraic solution of limits. And we say, what if I give you the limit as x approaches 3 of x squared minus 4x plus 3 over x squared plus x minus 12? Well, we already know that if the limit as x approaches 3 is in there, then the reason that the reason you can't just plug the 3 in is because you're going to get a 0 in the numerator and you're going to get a 0 in the denominator. Well, the fact that you get a 0 in the numerator and denominator means that each one of them must have a factor of x minus 3. So I went ahead without even thinking about it and said, oh, I know the denominator has a factor of x minus 3. I know the numerator has a factor of x minus 3. Now, in the denominator, what's the other factor? Has to be factors of negative 12. So I said, well, negative 3 times 4. And then just to double check, we know that the middle terms would combine to give me plus x, which is what that is. So I have my denominator factored. My numerator has to be factors of positive 3. So I said, well, negative 3 and negative 1. And then those would combine to be minus 4x, which is what that is. So now I have the correctly factored numerator and denominator for this limit. And I can say I still can't plug in the 3 because I would get a 0 in the denominator. But once I cancel out the factor causing trouble that's in common in the numerator and denominator, I'm going to be fine. So I cancel out the x minus 3's, and I can say this is the limit as x approaches 3 of x minus 1 over x plus 4. Now, the instant you can plug in the 3, that limit notation must go away. So a couple of things I'll be looking for in these, and you might have noticed in the instructions I said, please show all work. A correct answer is not worth full credit without the corresponding work. Some of the things I'll be looking for in this problem are that you carried the limit notation from the original problem to the second step, to the third step, and then when do you get rid of the limit notation? When you physically plug a 3 in for x, you don't write the limit anymore. So we're taking the limit by allowing x to equal 3, and you just say, well, okay, 3 minus 1 over 3 plus 4, your answer is going to be 2 over 7. Final answer there. Now, I would want that fractional answer as opposed to the decimal equivalency there. I think 2/7 is like 0.2857142857. Don't want that. Up next, we have the limit as x approaches 16 of x minus 16 over the square root of x minus 4. Now, you could have multiplied by the conjugate of the denominator to simplify this expression out, multiplied by the square root of x plus 4 over the square root of x plus 4. Rather than do that, I prefer to force a difference of two squares factorization in the numerator, because we know x is the square root of x times the square root of x. 16 is 4 times 4. So this factors by the difference of two squares formula as the square root of x minus 4 times the square root of x plus 4. Now, as x approaches 16, we know that this square root of x minus 4 can't stay in the denominator. Well, fortunately, it cancels with a factor of the square root of x minus 4 in the numerator. That leaves us the limit as x approaches 16 of the square root of x plus 4. Now I can physically plug the 16 in for x, so that limit notation drops out, and I get the square root of 16 plus 4. That's 4 plus 4 for a final answer of 8. The next problem is great because I'm going to give you one which it is not easily factorable in that denominator. A lot of people would struggle overwhelmingly trying to factor this. But we take advantage of the limit as x approaches 3. And he said, well, what do you mean take advantage of the limit as x approaches 3? Just as in number 7, I knew x minus 3 was a factor. Well, I know x minus 3 is going to be a factor in my numerator and denominator here. Now, in order to show it in the denominator, you could either use long division and say I'm going to divide x minus 3 into that, or what I've done here is synthetic division. If you have a solution or a limit at x equals 3, then let's synthetically divide with 3, and then you're going to synthetically divide that into coefficients 1, negative 5, 13, and negative 21. Please remember with synthetic division, the first number just comes down. Then you'll say 3 times 1 is 3, negative 5 plus 3 is negative 2. 3 times negative 2 is negative 6. 13 plus negative 6 is 7. 3 times 7, 21. Gorgeousness, because negative 21 plus 21 is 0. Now, what that tells me is that, yes, 3 is a 0 of this polynomial, which tells me x minus 3 is a factor. The other factor is going to be 1 degree less, and it's going to have the coefficients 1x squared minus 2x plus 7. So I use the synthetic division to show me what my denominator factors to. It would be really tough to factor that otherwise, but possible. Now, in your numerator, I factored out the x minus 3, and when I did that, I can just say, well, okay, I know that I have to have factors of negative 21 for the last term. Negative 3 times 7 is negative 21. We know negative 3 plus 7 would add to give me the 4x in the middle. So this is the correct factorization for the numerator. Once you have the numerator and denominator completely factored, we know it's the factor of x minus 3 again causing trouble. We cancel that out. We have left over the limit as x approaches 3 of x plus 7 over x squared minus 2x plus 7. You can allow x to equal 3. So from this step to the next, that limit notation must disappear. Your numerator is going to become 3 plus 7. Your denominator 3 squared minus 2 times 3 plus 7. And that gave me a denominator of 9 minus 6 plus 7, which was 10. Of course, numerator 10 as well, simplified down to be 1. So the limit as x approaches 3 of this function, nice answer of just a little 1 there. Up next, I want to make sure that you're confident with the proofs that will be on the test. Now, I've decided, since we're not meeting in person, I won't have any of the glorious fun proofs that I wish I could put on there. Like, there will be no product rule proof. There will be no quotient rule proof. There will be no 3-term product rule proof. There will be no prove the derivative of sine is cosine, prove the derivative of cosine is sine. None of the trig derivative proofs. The proof of the power rule that I looked at the beginning of 3.2, that's not going to be on the test. So none of those that I would normally test over are going to be on this midterm. However, I will put the 2 pretty straightforward proofs of the squeeze theorem proof and the intermediate value theorem proof. The squeeze theorem, I'll go ahead and tell you, the answer is 0. You have to use the logic of the squeeze theorem to prove that the limit as x approaches 0 of some product is going to be 0. So you have to prove it, and you have to use the squeeze theorem correctly in order to prove it. So how do you prove it? The problem with this original function, the reason you can't just evaluate it, is because this function does not exist at 0. And unlike earlier problems, there's no algebraic remedy to simplify that expression. So you say, well, as x approaches 0, that function exists, but what in the world is the cosine of e to an undefined power equal? Well, it doesn't equal anything. It's undefined at x equals 0. However, we know that that has nothing to worry about as far as the limit's concerned. There's a bunch of limits that exist that are undefined at the limiting value. All that we're concerned about is as it approaches from the left and right-hand side, it approaches the exact same value. So what I do know is that the only value this is undefined at is at 0. But everywhere else, that cosine function is going to be a number between -1 and 1. You always take whatever the trig of the ugly angle in this case and say, well, whenever it exists, it's a number between -1 and 1. This sets up our squeeze because now this -1 is going to replace it, multiplying the rest of the function. That's going to create the lower function. So the small function here, or the lower function, is x cubed times -1. And we're sure that that's less than or equal to x cubed times whatever the cosine is, because the cosine is always greater than or equal to -1. So this is always going to be greater than or equal to that, which in turn is going to be less than or equal to x cubed times the largest the cosine could ever be, which is 1. So now this is established our small function and our large function. Our function in between, it could be as large as this one, it could be as small as this one. Most likely it's somewhere in between the two. Well, now notice, if I can show that the small function and the large function have the same limit as x approaches 0, and you say, well, that's very easily done, John, because the limit as x approaches 0 of x cubed times -1 is equal to the limit as x approaches 0 of x cubed times +1, because in either way, it's 0 times a number that's -1 or +1. Thus, it's 0. Therefore, I can say the limit as x approaches 0 of the function that I was trying to prove is also 0. This is concluding your squeeze theorem. We chose a top function, we chose a bottom function, showed that they had the same value. The function in between also has to have that same value. Quod erat demonstratum. For number 11 here, anytime you're saying IBT, that's the intermediate value theorem. I'm asking you to use the intermediate value theorem to convince me, or to convince yourself, that x squared plus x has to equal 3. Okay, so the intermediate value theorem only applies to continuous functions. So I'm only going to give you a continuous function. And so you don't even have to state since the function is continuous. I wouldn't ask you to use it if it wasn't a continuous function. Now, due to that continuity, if I can find an x value that has a y value less than 3, and if I can find an x value that has a y functional y value greater than 3, then I know that my solution for x is somewhere in between my two x values. That's really easy to do in this problem, because please notice, if you plugged a 1 in for x, first of all, I'm letting f of x equal the left-hand side of this equation. So f of x equal x squared plus x. I need to show that f of x must equal 3. Well, f of 1 is 1 squared plus 1. It's 2. F of 2 is 2 squared plus 2, which would be 4 plus 2, 6. That's all I need to show. Since the y values moved from 2 to 6, as x went from 1 to 2, I know there's some value of x between 1 and 2 where the y value is 3. Now, technically, the way that the intermediate value theorem is worded is you're supposed to say, since f of 1 is 2 and f of 2 is 6, there exists an x equals c. The value of c is just the successful value of x. There exists an x value c belonging to the set of numbers between 1 and 2. A common mistake I see students make here is they'll say it's between 2 and 6. Those are y values. The solution for x is some number between 1 and 2, where f of c is equal to 3, and that's precisely what we needed to do. So I know there's some x value in between 1 and 2 that's going to have a y value of 3. Quod erat demonstratum, end of the proof. You don't have to put that, but I'd like it if you did. Next page here. For number 12, I'm looking at the higher derivatives, and I chose a fun problem here. I have the square root of x to the 9th minus 3 on the 9th root of x to the 4th plus 2x cubed. So I'm supposed to be able to take the derivative 4 times of that expression. That derivative process is so much easier if you get rid of the radicals. I need to understand that this is x to the 9 over 2 power. Remember, when you don't see an index on a radical, it's implied to be the second root or the square root. So you say, well, that's x to the 9 over 2 power. And then the next one is going to be minus 3. And then I'll have x to the 4/9 power. And then I'll have plus my 2x cubed. I didn't have to do anything with that one. Let's see if I can. Now, when I go into this next step, I can say, all right, so my first derivative, it's much better if you look at this. And I'll say the 9 over 2 comes down in front. X to the 9 over 2 minus 1 power, 7 over 2. For the next term, I said 3 times 4/9, that's going to give me minus 12 over 9. That reduced down to minus 4/3. X to the 4 over 9 minus 9 over 9 gave me x to the negative 5/9 power. Last term, I just said 3 times 2 is 6, x to the second. Now, each time, since the original was written in radical form, I want all of your derivatives also written in radical form. So this first one means this is the square root of x to the 7th in the numerator with that 9. This is the 9th root of x to the 5th in the denominator with the 3. So you see how I wrote that term, minus 4 divided by 3 on the 9th root of x to the 5th. And the 6x squared, you don't have to worry about it. You just rewrite it. So now, when I go to my second derivative, it's better to look at this and you say, okay, your first term, 9 times 7 is 63, 2 times 2 is 4. Your coefficient is going to be 63 over 4, x to the 7 over 2 minus 1 power is the 5 over 2 power. This term, you'd say, well, you're going to have a negative 4/3 times a negative 5/9. 4 times 5, it's going to give me plus 20 over 27. X to the negative 5 over 9 minus 9 over 9 gives me negative 14 over 9 power. This quadratic has a derivative that's a linear. 6x squared becomes 12x. And then you can see how I rewrote it. This is going to be 63 times the square root of x to the 5th in the numerator over 4. And then this is going to be plus 20 over 27 on the 9th root of x to the 14th in that denominator, and then plus our 12x. For the third derivative, so we say, well, okay, these just keep on multiplying. 63 times 5, 60 times 5 is 300, 3 times 5, 15, so that's going to be 315 over 8. X to the 5 over 2 minus 1 power, 3 over 2. Your next term here, and they don't simplify, negative 14 times 20 gave me negative 280. 9 times 27, I was just thinking 27 times 10 is 270 minus 27 is going to be 243. 243 in that denominator. Of course, a negative times a positive made that a minus 280 over 243. And then x to the negative 14 over 9 minus 1 power gave me negative 23 over 9. Derivative of 12x, 12. For the fourth and final derivative here, just said 3 over 2 times 315 over 8. That gave me 945 over 16. Subtract 1 from the exponent, gave me x to the 1/2. The next term, I did just go to the calculator. I knew it was going to be a negative times a negative, so it's going to be a positive. For my numerator, I don't think that my calculator dealt with these fractions well, and I wanted to leave it an exact fraction. So I just went in and said 23 times 280 for that numerator. And I said of course, 9 times 243 in the denominator to get that. So I just did the fraction that way. I think when I tried the 280 over 243 times 23 over 9, it did not work. It gave me a decimal, which it was not able to convert to a fraction. Oh, no, it did now. Well, my calculator's proving me wrong, but I'm pretty sure it didn't earlier. You might check to make sure your calculator can do that. I'm pretty sure I was using a calculator that couldn't, so I just multiplied it the other way. But either way, you get to the exact coefficient, and then the power drops from the negative 23 over 9 power minus 1. Negative 23 over 9 minus 9 over 9 gives me negative 32 over 9. And then please notice the third term becomes 0 because the derivative of any constant is 0. When you rewrite the final term, this x stays up in the numerator. You're going to have 945 on the square root of x to the first over 16 plus 6,440 over 2,187 on the 9th root of x to the 32nd in that glorious denominator. Now, I know what you're thinking. You're thinking that was a cool problem. It really was. Loved it. Up next, we have the vertical position function problem, where I give you a position function, in this case 544t minus 32t squared, and I ask you to find the maximum height, and then I ask you to evaluate the velocity at a given height, and that given height is going to be a height on the way up and on the way down. Okay, so now, first of all, the maximum height, and I need to show the maximum height with calculus. The way to avoid the calculus, you could just say, well, John, I know the vertex of a parabola is at negative b over 2a, so can't I just use that? Nope, I can't use that. I've got to go in and show that I can at least take the derivative. So the derivative of the position function is the velocity, and that's very easy, taking the derivative. You just get your 544 minus 64t in this case. Now, we know that that maximum height occurs when a velocity is 0. All the way up, it's going to have positive velocity. So positive velocity all this way, negative velocity on the way down. At the instant it's at its maximum height, it's going to have a 0 velocity. So I can say, well, I set that velocity function equal to 0. That gave me 544 is equal to 64t. Thus, t is equal to 544 over 64, which is 8.5 seconds. Now, that's not the answer. This is just when the maximum height occurred. So I had to take that 8.5 seconds, plug it into your position function. The position at 8.5 seconds is 544 times 8.5 minus 32 times 8.5 squared. That gave me 2,312. And I wanted to put the units in this problem. The height is measured in feet. So please do put the units since it is an application problem. So that maximum height occurs at 2,312 feet. Now, the second part of this, part B, I ask, what is the velocity at 1,920 feet on the way up and on the way down? In order to answer that question, it's probably helpful to at least find the times using your calculator. Alternatively, you could have said 544t minus 32t squared equals 1920 and used the quadratic formula or something like that. That's not calculus, so I don't care how you solve for when that's equal to. So setting the position function equal to 1,920, I have no preference how you do that. I just use the calculator. Again, quadratic formula would be fine too. I'll say 544x minus 32x squared. And then my y2, I needed to find when the position is 1,920. So now, I already know that the maximum height is at 8.5, and that occurs at 2,312 feet. I did that without having to graph anything. So when I go to my window, you can say, well, we're talking about time. X should never be anything less than 0. And you can bet you're going to, if it takes 8.5 seconds to go all the way up, and we know that the original position, if you plugged in S of 0, you get a 0. Original position is 0, 8.5 seconds, it reaches its maximum height. It's going to come back down to the ground in another 8.5 seconds. So logic just told me to say, well, how about I set the time from 0 to 17, double whatever the time it took to get to the maximum. And then for the y values, zoom 0. You'll see your position function going in here. See that maximum height. Now, if you hit trace, you'll see that maximum height, 8.5 and 2,312. It's a good way to check yourself. But now I need to find the 2 points where it's equal to 1,920 feet. That's what I entered in to Y2. So on that graph, I need to calculate second trace. I need to calculate where these curves intersect. Second calc, you can arrow down to 5 or just hit 5. And it's asking first curve. We hit enter. Second curve, enter. Guess, just hit enter again. And it's giving me the ordered pair 5, 1,920. Now, just getting that one, I already know what my other point is. If it took 3.5 seconds to get from 1,920 feet to 2,312 feet on the way up, it's going to take another 3.5 seconds for it to get from this 2,312 feet to 1,920 feet. So I already know that all I have to do to find this x value is to add 3.5 to 8.5, and it's going to be at an x value of 12. If I didn't use that logic, I could still use the calculator and say second count 5. I still hit first curve and second curve, but when it says guess, if I just hit enter again, I'm going to keep on getting this answer all day. So when it says guess, just arrow over to the other point and hit enter, and it will show you, hey, yeah, you have an intersection at 12, 1920 as well. So now I have my 2 times at which the height is 1920. Now, the logic that I'm wanting you to understand here from a physics standpoint is that the only force acting on this object that's being shot up and then coming back down, it's gravity. So the same gravitational force that slowed it down from its positive velocity to 0 is the same gravitational force that's going to speed it up in a negative direction from 0 to its velocity at this point. So I know that the velocity at these 2 points must be equal and opposite. Let's show that. Evaluate your velocity function at 5. Well, the velocity function at 5, here's your velocity function. 544 minus 64 times 5, you get 224 feet per second. Now, before I even did the second one, I was 100% sure that the velocity at 12 seconds had to be negative 244 feet per second. There's no question, it has to be. But of course, you can plug it in and convince yourself of that as well. And say the velocity at 12 certainly will be negative 244 feet per second. Now, for number 14, I will give you a graph of some parabola that will be the derivative of an original function, and then ask you information about that original function. Okay, so for example, here's the parabola f of f prime of x. It's a negative parabola with x-intercepts at -3, 0, and at 1, 0. So what I need to know about a derivative, whenever a derivative is negative, the original function is decreasing. Whenever a derivative is positive, the original function is increasing. And of course, negative again, the original function is decreasing. Whenever a derivative has x-intercepts, that's telling you that the slope on the original function is 0. It could have a maximum or minimum value at any x-intercept. And if the original function does have a maximum or minimum value, the derivative certainly has an x-intercept. So now when I'm asking you when f of x is going to be increasing and decreasing, and actually the first thing I did, and you can see it by the order of what I did it, as soon as I draw out the derivative, I wanted to go ahead and draw the original function, and then it's easier to answer parts A and B. So go ahead and graph the original function given this derivative. And I will give you some other criteria, like the original function has to be 0 when x is 0, so it's going to have to cross the origin. Now, so whenever I drew this in order for the original function to cross the origin, I just had to make sure that this derivative, I knew that this derivative told me that the original function, it's going to be always decreasing from -infinity to -3, and it's going to flatten out at -3. So I just needed to show that it decreased down to x equals -3, and -3 had to be a negative y value in order to have that 0, 0 point. Now, could I have given this, if I didn't say f of 0 had to be 0, could have I had it decreasing to x equals -3 up here? Sure. And then going up from there. All you know from this is that at -3, you have a minimum. It's going to be decreasing before that and increasing after that. Now, from -3 until 1, that derivative is positive. So the original function has to be increasing from -3 to 1. So from x equals -3 to x equals 1, my original function increases. And I also want that extra stipulation of f of 0 is 0. Okay, I've got that. I have it increasing, and it's going to flatten out at x equals 1 because the derivative becomes 0 at x equals 1. Now, what happens to the derivative after x equals 1? Turns negative. Thus, the original function is going to be decreasing. the more negative this is, the steeper negative slope this is going to get. And so you say, okay, that's going to be fine. Now, this perfect graph for the original function given this derivative, well, not perfect, but a good graph. And then I can say f of x is going to be increasing. Please don't just look at this. I'll have students that'll try to guess what this maximum here is and say, oh, it's increasing from negative infinity to negative 1. No, bad, bad, bad. It's when f of x is increasing. You say, well, the only time f of x is increasing is between your two x values, or it's when the derivative is positive. That's from -3 to 1. So f of x increases in interval notation from x equals -3 to 1. It's going to decrease from negative infinity until x gets to -3, and then from 1 off to infinity. We know clearly just by looking at it, it's going to have a minimum at x equals -3. I don't have a clue what the y value of that minimum is, nor should I. The derivative doesn't give us the specific y values of the original function. Since the derivative represents the rate of change, it's representing the shape of the original function. But this function and a function shifted down 1,000 units or up 1,000 units would all have the exact same derivative. So the derivative is just going to be the shape, not the specific y values. So all I can say is that, well, I know that there is a minimum at x equals -3, and I know that there's a maximum at x equals 1. Okay, now I'll go ahead and take a pause here and do the second part of this practice test in another video, because I'm afraid this is getting too long for my Zoom. But please do check out part 2 for the continuation of this. This is good stuff. Fun, fun, fun. All right, guys, and please, of course, let me know if you have any questions.